Doppler effect is this. So first I'm going to show you one video, and also first let me state what is Doppler effect. So for example, if you are making some sound, let's say if you are making sound of some pitch, right, say 400 hertz, right? And if if your friend is standing a little further away, right, at rest, let's say, your friend will exactly hear 400 hertz, right? If you both of you are standing, right, not moving. If you are making 400 hertz noise, right, sound, your friend will exactly detect 400 hertz as 400 hertz, right? But that's not true. If now there's some relative motion between you and the detector, okay? So, and that apparent change in the frequency of the sound due to the relative motion between source and listener, right, is called Doppler effect, also called Doppler shift, right? So that's basically Doppler effect, okay? So Doppler effect is the apparent change in the frequency of sound due to the, relative motion between source of sound and listener, right, observer, is called Doppler effect. And this is all explained by this in this animation, see? So you're standing here, the ambulance approaches. So what do you hear, right? We see in everyday life actually. When a vehicle approaches you with some siren, right? You hear high-pitched sound, right? When it approaches towards you. But as it passes by, what do you hear? The pitch will decrease, right? Right away you can hear that. The pitch of the sound will decrease right away as the vehicle actually, ambulance pass by you, right? And that shift is called, this is basically Doppler effect. And this is because of this actually. You can see the wave front, these waves, right? Wave front, you can clearly see, right? As it is approaching you, all the wave fronts are compressed, right? Because since the ambulance is moving towards you, right? The wave fronts will be compressed. But when it passes by you, all the wave fronts will be, stressed out, right? Like this. That's why you hear different pitch, different frequency than original sound frequency. And that's Doppler. So let me quickly actually turn this video on, showing actual change in pitch of the sound. Pitch depends on the frequency. Right? You clearly observe right here the difference in pitch, right? As the vehicle approaches towards you and as it passes by you, you can distinctly, hear the change in pitch, change in frequency of the sound, and that's because of Doppler effect. This is called Doppler shift. And keep simple, actually, we can just quote the formula. We don't need to derive all these formulas. We can derive, but we don't need to derive this formula. This is the formula we have. So this is the formula for the frequency detected by the listener, okay? Or you can also say the apparent frequency, right? Detected by the listener. L means listener. So F of S is the original frequency of the sound, right? Original. And here V, without any suffix, V is the speed of sound in air. That will be standard, that will be given. Usually is 343 meters per second is the standard, speed of sound in normal air and normal pressure. And V of L is the speed of the listener or observer. V of S is the speed of the source, okay? And this plus and minus, both plus and minus, depends on whether the source is moving towards you or you are moving away from the source, right? It depends. You'll have to determine that for the given problem. And so by, just by common sense, what will happen if the source of sound is moving towards you, the apparent frequency will increase, right? If the source of sound is moving away from you, the apparent frequency tends to decrease. And based on that, you have to choose plus and minus sign, okay? Based on that, just by using common sense. So let's see. So these are some examples. So this is your main equation, and this formula will also be given to you. This formula will be given to you on the formula sheet, right? You can check. And here's what you need to do. If the listener is moving towards, right? If the listener is moving towards the source of sound, you have to use positive. Why? Because the apparent frequency increases, tends to, right, increase. So plus will guarantee that. And however, if the listener is moving away, you have to use one negative sign because it's in the numerator. And in the denominator, it goes opposite. If the source is moving towards, right? If the source is moving towards, the apparent frequency increases. And to guarantee that, you need negative sign here, right? Because denominator, right? If you make less, the whole thing will go up, right? So if source is moving towards the listener, you need negative sign here. However, if the source is moving away, right, you need positive sign because that will decrease the apparent frequency, right? So that's it. That's all you need to do in solving the Doppler problem. And some problems will be a little tricky, but this is the main idea of solving. So in this one is the frequency the listener will hear at given, right? So just a second. Okay. So this is the main idea. So now let me show you a couple of animations. So if there's no relative motion between source and listener, right, there will be no Doppler shift, as I explained, and right, it will detect as original frequency. But let's see, if a source of sound is moving towards you, see how the wavefronts are compressed. So the observer will find out a higher frequency than the original frequency as expected. Why? Because see the number of wavefronts per second has increased because of the compress, right? Because the source is moving towards you. See how apparently, right? Apparently, the frequency of sound increases, right? For the observer, and the opposite will happen. If the source of sound is moving away from the listener, the apparent frequency decreases, right? Because less number of wave pulses, right, are coming per second. See, right?
Excuse me, Professor.
Yep.
You might be about to show this, but so that is the Doppler effect only occur if the source is moving, or does it occur if either the source or the listener is moving?
Yeah, either the source or the listener is moving, both.
Okay, thank you.
Yep. Okay, and these are the cones actually. So see, if these are the thing we have just discussed, right? But what happens if a source of sound moves with exactly with the speed of sound? The wavefront would look something like that. Okay, it's also called shock wave. If an object moves with the speed of sound or faster than the speed of sound, it is called shock wave, right? It's called shock wave. See this cone, it's shock wave because now all the wavefronts, if you're a listener, right, somewhere here, all the wavefronts approach towards you at the same time because all the wavefronts meet constructively, right? And it approaches you, right? It hits you at the same time, all the wavefronts, right? And then you will hear a big noise, and it's called sonic boom. That's why it is called sonic boom, right? And obviously because all the sound energy reaches you at the same time, right? And it has a very powerful sound. It's a very powerful because it's a compressed ear, very compressed ear, right? It's called sonic boom. Okay, sonic boom is supersonic, and that's also called shockwave. And here's an example. So this is the sound shockwave produced during supersonic. So it was this rocket-propelled, vehicle is traveling faster than 800 miles per hour. That's the supersonic, right? Because in miles per hour is about 700 something. 700 miles per hour is the sonic speed, right? And in 1997, somebody broke this record, and you can see the distortion of the landscape, right? Right here, you can see this shock wave. That's because of the compressed sound wave, actually. That changes the density of the air, right? And that's why you can see the distortion of the landscape because of the compressed air, because shock wave is moving right here. And that causes the sonic boom. And but you don't need to, the object doesn't need to be traveling at super fast speed to observe the the shock wave. So for example, water waves travel very slow actually compared to sound wave, right? And the boat could be moving a lot faster than, you know, the water waves. And you can clearly see the shock wave. This is shock wave. See the conical shape, right? That's the shock wave actually, see, right? And let me show you one video on the shock wave, which is sonic boom, right? So
all right. There they are. Coming in like meteors, real fast. They're going to do a final burn here in just a moment. There's final burn 1 and 2. 2 candles coming down.
there they are.
Double sonic booms.
Booms, right? So that's because of the same science behind that, because all the wavefronts constructively, you know, interfere and approach towards you at the same time, all the compressed wave. And that is, you know, you will hear that as a sonic boom. So, you know, a very powerful sound. Okay, so that's all about the Doppler effect. And one more thing, Doppler effect also works as in light waves as well. Okay, you just need the theory called special theory of relativity from Einstein, Einstein's special theory of relativity to derive the formula for Doppler effect in light. Light means electromagnetic wave, right? And that's how the astronomers, physicists found that, you know, our universe is expanding. And that's how they use the technique called Doppler shift, because the light from the distant stars, right, is, you know, has a red shift. That means its wavelength, right, its frequency or its wavelength has shifted to red part of the spectrum. It's emitting frequency lower than it's supposed to. So that means the distant stars and galaxies are moving away from each other. So that's how, and this has been tested again and again actually. So our universe is actually expanding actually. Okay, and that's how it is. It's called red shift. Okay. All right, so that's all about the Doppler shift, Doppler effect, and then now we're going to do some problems to understand all this. And this Doppler shift is also very useful in the radar gun, right, to measure the speed of, say, the speeding car, right? The police uses the radar gun to measure the speed of the speeding car. So how does it work? It uses the same principle actually, Doppler shift. It just measure the shift in the frequency, right, from the original frequency, and just by measuring the shift in the frequency from the reflected off the car, you can actually calculate. It calculates the speed of the moving car. Okay, so let's do some problems now based on this. So here's the first problem. Just to get started, we're gonna do with the simple one. So this is the first problem I'll be showing you. Okay. So here's the first question. This is the end of the chapter problem from my lecture slide. Let's see first. So here's the question. It says, a friend of yours is loudly singing a single note at 400 hertz, right? Is singing at 400 hertz and approaching towards you, okay? It's while driving towards you at 25 meters per second on a day when the speed of sound is it says to use 340 as the speed of sound. What frequency do you hear? You're at rest, right? And what frequency does your friend hear if you suddenly start singing at 400 hertz, right? And what frequency does your friend hear if you suddenly start singing at 400 hertz and moving towards your friend with 10 meters per second? So these are the questions, you know. So let's use the Doppler formula, right? So let me go back and try to solve some problems based on that. So here's the So here's the Doppler effect problems. So that particular problem for my lecture slide, it says, so here's the question. So this, let's say you don't need to draw all the pictures. So you're a listener right now, right? Your friend is driving towards you. So your friend is the source, right? Your friend is driving towards you at what velocity? Velocity of what? Velocity of 25 meters per second. So initially you are at rest, right? So what frequency, and your friend is emitting 400 hertz as the original frequency. This is f of s. F of s is the original. So what frequency, what apparent frequency, you have to say apparent frequency, right? Do you hear? And that's pretty easy, right? So the apparent frequency that you will hear is based on this formula, f of s, right? That's the original frequency. This is the apparent frequency. So now you have to adjust these formulas. So remember, let me first write down the formula. This is the formula you have, right? Listener in the numerator and source velocity in the denominator. This is the speed of sound, which is given. Okay, now this is 400 hertz. That's the original frequency. The speed of sound is 340. That's what it says to use. And the listener is now approaching, no, listener is you. You are at rest, so 0, right? So listener is 0 because you are the listener. So now source is moving towards you. So do you use plus sign or minus sign in the denominator? The source, which is your friend, right, is moving towards you, right? So, and we know when source is moving towards you, the apparent frequency has to increase. We know from common sense, right? If source is moving towards you, the apparent frequency will increase. So to match that, so what actually sign do you use? Plus sign or negative sign? So tell me, do you use plus sign or negative sign?
Negative sign.
Negative, yep. Why? Because it's in the denominator, right? And making minimum in the denominator makes the whole thing maximum, increase, right? Because we know that the apparent frequency will increase. We know that from common sense because it's approaching. Okay, that's it. That's it. So it's 340 minus, and it's approaching at 525 meters per second. So that's your answer. So do that calculations. So 400 times 340 divided by 315, right? Okay, so it's 432 hertz. So you will hear that sound as 432. Even if the original frequency is 400, you will hear that frequency, right, as 432. The apparent frequency increases, right, as expected. That's part A. So part B. Now it says, part B says, now what frequency does your friend hear if you suddenly start singing? Now you are the source, right? Now second, it's different for different problems. Situation is different for different problems, right? Now this is the scenario. Now you still at rest, but now you're singing sound at 400 hertz, right? And your friend is still approaching towards you. Your friend is now listener. Your friend is listener, okay? And is approaching towards you at 25 meters per second, right? Now you are a source because you are singing, and your friend is listener, okay? Situation has changed. Now what apparent frequency does your friend hear, right? Apparent frequency heard by your friend, right, is now same thing. So just match plus and do play with that formula, right? So now from the given equation, so your listener, right, listener is approaching towards, so V plus VL, right, because it's approaching towards, and your source is at rest, your source now. That's it. That's your equation. So this is still for, because you are singing at 400 hertz. So this is the speed of sound. So V is, don't get confused, it's the speed of sound in the given medium, in the air, right? It will be given to you. Plus approaches is still approaching at 25 and 340. That's it. So that's the frequency that your friend will hear, 400 and 365 divided by 340. So 429, slightly different, but it still increase. Okay, now that's it, right? That's simple. And now next scenario, part C, is now like this. Now both are moving. You, right, still singing at 400 hertz, but you are now moving towards your friend at 10 meters per second. You are still source. You're still source. Your friend is approaching towards you at 25 meters per second. Right? Still listener. Now, what frequency does your friend hear? That's what it says, right? Who is the listener? So what frequency does your friend hear, right? Your friend is still listener. Okay, now you have relative motion, both relative motion, right? Both are moving towards each other. So now again match that, so F of S. So listener is moving towards, so you need plus sign. And source is also moving towards, right? So you need to minimize it here. So that's it. So this is again 400 hertz, 340 plus the listener is your friend 25. However you are moving with 10 meters per second. Okay, so that's the apparent frequency that your friend will hear. Okay, it's going to be 442. And apparent frequency has increased, right, by 42 hertz still. Okay, so that's how you just need to play with this formula, main formula. Just need to understand which one plus and minus use, you know. Any question? Any question? Okay, let's do little tricky one. So that's number 2 is similar. Number 3, let's read number 3. Number 3 says a police car with its 400 hertz siren is moving away from the warehouse, right, at a speed of 40 meters per second. What frequency does the driver of the police car hear as reflected wave from the warehouse? I mean, you can call it echo, right? So it's just asking what echo frequency will the driver of the police car, right, hear from the warehouse? Warehouse is a kind of reflector, right? It's the wall of the warehouse, act as a reflector of the sound. Assuming that air is still and the speed of sound in air is that. So here's the hint, main idea. The wave fronts, right, the wave fronts are reflected from the wall of the warehouse at the same rate that they are incident on it. So that's the main idea. Okay, so let me try to explain what that means. Okay, now next problem, little tricky. So this is number 3 from my lecture slide. Okay. So question is, so this is the warehouse wall, let's say. I'm just drawing this. And this is the police car, right? It's moving away. Police car is moving away, but it's making sound which gets reflected off the, right, like this, and it's asking what echo frequency, right, will be heard by the police. Right? This is the warehouse wall. Okay, first we have to, now the main idea is the wall will reflect the sound wave at the same rate that it incidents on it. Okay, that's the main idea, the hint. The wall will reflects this wave at the same rate. Rate means frequency, as it is incident on it. That means, so what frequency does the wall hear? So let's say wall is listener now. In first case, wall is, you can break into two parts. Wall is now listener, because we want to find out what frequency will be detected by the wall, right? And it will be reflected off by at the same rate. That's how the wave behave. Okay. Now, first case is wall is listener, and the car is source. So we want to find what frequency will be incident on the wall, right? So this frequency, right, is now based on the, so V is speed of sound. It says to use 343, right? So V, now with listener first, right? So listener is wall is at rest. So V, and the car, police car is the source, right? Car is the source, but it's moving away. So away means you need plus sign. Police car, right? Source is the car here. Okay, now let's first find that out. The original frequency is what's the original frequency? 4.5 Hz siren. So 4.5 Hz. And 343 divided by 343 plus, what's the car speed of the car? Speed of the car is 40 meters per second. Okay, so this is the frequency that will be incident on the wall warehouse. Okay, so first find that out. So 400 into 343 divided by 383, right? And that's going to be 358 Hertz. And again, now I'm going to use this idea, this hint here. See, the wall reflects the wave at the same rate, at the same frequency as it is incident on it, right? That's what I gave you as a hint, right? So this 350 Hertz is the frequency of the sound, which will be incident, which hits the wall. Now, second part. Now, wall is source, right? Because we want to now do one more Doppler shift, double Doppler shift. Because now wall, now for the police car, right, which is moving away. Now, wall works as a source of sound because it's reflecting the sound, right? But the listener is moving away now, right? Now, in second case, now you have to switch the role. So now police in the car is listener. And the wall, the warehouse wall is source because it's reflecting off the surface, right? It's reflecting the wave. So wall is source and police is the listener. Now, finally, second, it's called double Doppler shift. Now, what will be the frequency? Now, source emitting that much frequency. Wall is the source of sound, which is emitting F1 Hertz, F prime Hertz, which is 350. So you have to now use the original sound wave as F prime because that's right. That's that works as the original frequency now because wall is reflecting right at that rate with that much original frequency. So V now police is moving away, right? Police is listener moving away. So VL divided by wall is at rest. So VS is 0. And that's your final answer. So this is now 358. That's the little trick. That's all. So listener is, car is the listener, which is moving away at 40 meters per second, 343. That's it. that's the final Doppler shift. So, so problem like this echo problem, you have to do double Doppler shift, right? One, listen by the wall, and again, when it reflects back, you will have one more Doppler shift. So 358 times 343 minus this, right? And divided by 343. Okay, 316 Hz in 360. So that's the frequency heard by the driver in a police car. Finally. So you can clearly see, right, what's the original, very original frequency? 400 Hz. That's the siren frequency, right? But the driver in that police car will hear only 316, huge shift, right? 316 Hz. And because the main reason is it's moving away from the wall, and there's a double Doppler shift. So that's how you, and this is called echo actually. Echo frequency. So whenever you solve echo, make sure you have to do double shift, double Doppler shift.